everyone, welcome back. Today we're going to talk about, derive, and use elastic potential energy. And we are going to start with the force spring versus displacement graph that we created when we talked about spring constant. And just like the other types of energy, we're also going to derive this from the work formula, which is the transfer of energy to or from the system. So to start, I'll move this over here. I'll move this over here so we can work with it. And since actual values sometimes help people visualize things, I'm going to create another line here. So now we have two springs, the blue spring and the purple spring. The blue spring, it was difficult to see exactly where the numbers hit, so I wanted to make one that came out cleanly. Now, a few reminders. One, the slope of this line equals a spring constant, which has the units newtons over meters. The second is going to be brought up during this derivation. Now, since work is force parallel times displacement, and if I have a spring, and I want to stretch it, let's say this part's touched to the wall, I will grab it and force hand on spring pulls to the right. And then displacement will also be to the right, so we have a parallel force and a displacement with a force that is parallel to it. However, if I'm holding the spring at this length, I'm holding it with force spring at that length. So force spring will be negative k delta d. Now, something to keep in mind is going to be important here. Force spring represents this force. Force hand on spring is this one, which technically should be drawn here now. So force hand on spring and force spring on hand have the same value and are in complete opposite directions. Force spring is to the left, force hand is to the right. That's going to be important for this. Now, this force matches this value, both of them. And for my purple spring here in my diagram, that is 20 newtons right here. Now, this force parallel is an average force, and you did not use 20 newtons to stretch it the entire distance. Just before touching the spring, it was 0, and as you pulled, that force got larger and larger and larger and larger, so this is not a constant force. And since this is a linear relationship, what is the average force you used? Well, the average force you used would be dead center. In this case, it would be 10 newtons. And since the initial force will always be 0, and you're stretching it to that final point, that means my force parallel is actually 1/2 force spring delta d. So that means my work equation is actually 1/2 force spring times delta d. Except the truth is, it's not actually force spring. It's 1/2 force hand on spring delta d, because it is the force you are using to pull the spring to the right. And remember, these two are third law pairs. Now, the only difference between force spring on hand and hand on spring is the direction, which means I'm using this formula without the negative sign. And I get 1/2 k delta d squared. This is the change in elastic potential energy. So to put it more simply, it is the average force times the displacement. Since the force starts from 0 and goes to a final value, the average is dead center between the two. And since the initial is always 0, the average force is half the final value. So it is 1/2 force spring times the distance. And the negative sign is removed because you're dealing with the force you are exerting on the system, not that the system is exerting on you. And here we have our formula for elastic potential energy. And just to note, since we basically just did 1/2 height times base, the energy stored in the spring is also represented by the area under this line. I'll put it here to reference. And a quick note, capital U is a symbol for stored energy, and S stands for spring. I know it's elastic potential energy and should be E, but E was taken up by electrical potential energy, which we may be discussing later. Okay, so let me show you how this equation can be used. Here is a problem involving elastic potential energy. And I'm going to skip the simple you're missing one variable, solve for the others types. I'm going to go right into an energy transfer question. A 2-meter long spring with a spring constant of 50 newtons per meter is scrunched to a length of 0.5 meters in order to shoot a 0.18 kilogram ball across the room. At what velocity will the ball leave the spring? I'm going to start by drawing my situation. Here's my spring. I'm going to have my bar graph over here, and of course my elastic potential energy equation. My system will involve the objects that actually obtain energy. That will be the spring, because that will start with elastic potential energy. Now, when the spring fires the marble, it will give all its energy to the marble as kinetic energy. So it is all being transferred, which means the ball, or marble, is going to be my other object here, which means I can write a relationship directly between elastic potential energy initial and kinetic energy final. Now to list my givens, I'm going to listen for the spring and the ball. Displacement initial for the spring. Now the displacement of the spring, since it is being brought back to 0.5 meters, is going to be 1.5 meters, technically negative 1.5 meters. Displacement final for the spring will be 0 meters because it will be back to its original length. For the ball, we have a mass of 0.18 kilograms. VI equals 0 meters per second, and VF is our unknown. Now I'm actually going to solve this using the two parts. Elastic potential energy initial, 1/2 K delta D initial squared, 1/2 times 50 newtons per meter times negative 1.5 meters squared, and of course this negative is going to cancel out when this number is multiplied by itself. Hence, it does not matter if you stretch or scrunch a spring, you are storing energy in it either way. I do this and I get a value of 56.25 joules. Now that means since initial elastic energy equals final kinetic energy final in the ball is going to be 56.25 joules. I take my kinetic energy formula and I will rearrange it for VF. That rearrangement will be 2 times kinetic energy over mass square root 2 times 56.15 joules divided by 0.18 kilograms. I get a final velocity of 25 meters per second. Keep in mind, technically the screw spits out a positive negative, which means this marble could be fired in any direction. So you got to keep on that visually. Based on our picture, our marble would be fired to the right. So this demonstrates an energy transfer question. This started with elastic potential energy in the spring, and then that energy was transferred to the marble as kinetic energy. And as a note, I literally could have used this relationship, rearranged it, and solved it from there, but I wanted to show you the actual energy values as we went through. Now, the next thing I wish to do is take this near exact problem, but show you how it can be given to you in a higher difficulty level. I start out the same way. A 2-meter long spring with a spring constant of 50 newtons per meter is scrunched to a length of 0.5 meters in order to shoot a 0.18 kilogram ball across the room. What velocity will the ball have when the spring is 1.4 meters long? This is the difference. We are finding the velocity of the marble before it actually leaves the spring. So let's start with a drawing again. This is scrunched to 0.5 meters. This is the initial state. Initial. The problem is not over when the spring comes to its relaxed length. As soon as the spring is 1.4 meters long, this problem is over. So the ball is pulled back, just like in a pinball machine, held here, is fired, and then at this point, the problem is over. Velocity initial of the marble is 0 meters a second. Velocity final of the marble is our unknown. Now for my spring here, I have delta D initial is 1.5 meters, just like last time. But I also have a delta D final, which is 0.6 meters, because displacement of the spring is how far it is stretched or scrunched from the rest position. My delta D is not from here to here. Mass of the marble, 0.18 kilograms. My system again is a string and the ball, because those are the two objects that will actually have energy. All right, initial state. I have all the energy stored in the spring because it's scrunched all the way. Final state. I have kinetic energy in the ball, and I have some energy still left in the spring. So let's break this down. 1/2 K delta D initial squared, 1/2 mass of the ball V final squared of the ball, 1/2 K delta D final squared. So there's something I want to show you here. I know I could cancel out the halves, but I'm going to move this over to start. I now have this expression with my final elastic potential energy on the left-hand side, and I'm going to factor out the half and the K. And the reason I wanted to show you this is to really point out what I have underlined here. You cannot simply use the displacement from the initial point to the final point here. Elastic potential energy is in a squared relationship with displacement. It is not linear. The more you push back the spring, the larger the force is, which means there is more energy stored in this small distance than this small distance because you're farther back on the spring. So in other words, when dealing with the initial state and final state of the spring, you literally have to write out that subtraction and then solve for it. In the last problem, we didn't have this because the final displacement was 0, so it canceled out anyway. As a side note, for something like gravitational potential energy, if you double the height, you double the energy, because these are all linear relationships. Again, displacement for elastic is not. So I will continue this. The halves cancel, and Vf equals K, quantity delta di squared minus delta d final squared over m. 50 newtons per meter. Now notice my initial value is larger than my final, 1.5 meters squared minus 0.6 meters squared over mass 0.18 kilograms. Now going back to our previous problem real quick, we got 25 meters a second when this ball left the spring entirely, which means all the energy was transferred. In this problem, the ball has not left the spring yet, so not all the energy is transferred to the ball. Some of it is still in the spring. So we should expect an answer that is lower than 25 meters a second. And if we calculate this, we will get 22.9 meters per second. So this does not raise a red flag for us. This is around the area we would expect for an answer here. And there you have a complete elastic potential energy question. Okay, there's one more thing I wish to show you. This is Hooke's law, and this is treated absolute value, but this is the force versus displacement graph that we've made a few times already. As I pull the spring back, the force gets larger in a linear relationship. We already mentioned the slope is the spring constant, but the area stored under this line is the work done, because work is force times displacement. More specifically, since the work is done storing energy in the spring, the area under this curve is the elastic potential energy. Now, something I want you to notice, if I cut the distance in half here and do a little geometry, I will get 4 equally sized triangles. Each one of these areas represents an equal amount of energy. Now, if I take that spring and draw it back a certain distance, I will get this much energy stored in it. If I double that distance, however, I get the rest of these combined. So literally, if I double the distance, it would be 4 times the energy stored. Hence this squared relationship over here. This on the right is an elastic potential energy versus displacement graph for the spring. Notice the curve because of this squared relationship. If I mark the end and mark the center here, drag this to the right, drag this to the right, I get this much energy versus this much energy, which if you look at it is about 4 times the initial. And something else I'd like to show you while I'm here. I'm going to cut this into fourths. Now, this is 0 meters, 1/4, a half, 3/4, and the full distance. If I stretch that spring, this much energy is stored in the first quarter of the stretch. However, this much energy is stored in the fourth quarter of the stretch. So in other words, this distance and this distance is the same. However, the last quarter distance has a lot more energy than the first quarter distance because as you pull the spring back, the force gets larger. So going back to my basic work equation, there is more force in the last bit of the stretch than the first part. Therefore, there is more energy stored. This is also why you cannot just subtract the distances if that spring is not fully released. You actually have to find the initial energy stored, final energy stored, and literally find out how much has left the spring. All right, I'll end this here. Have a good day. This is Mr. M, signing off.